Hello, it appears that something happened to week six's recording, so I'm going to do a quick recording to put this up for those that weren't able to join live. Jumping straight in, the agenda for this discussion is around the assignments, the reading, and then we'll talk a little bit about Spark and Databricks, and this is relevant for your current assignment because I do allow you to use Databricks for this assignment. We probably won't have time to talk about APA topics, but anyway, we are into Unit 6. Unit 6 centers on things like Hadoop and the tools that support Hadoop. Hadoop is an ecosystem unto itself. There's lots of different technologies involved. We've touched on some of them before, such as MapReduce, Hadoop distributed file system, and so on. We are making our way through this unit. Your individual project for Unit 6 is due on Sunday, so keep that in mind. Unit 6 does center on Hadoop. Hadoop's been around for quite some time. It's not as popular as it once was, but it's still relevant, especially relevant from a discussion of how we got to where we are. So do keep that in mind. It's not something that's totally out of date. There's still instances of it, but you'll find that there's very few new installations being created for Hadoop. Your assignment, your first discussion board, is to compare and contrast the methods used in traditional data management to those used in essentially a big data environment such as Hadoop. And your discussion should also talk about the advantages of parallel processing. What that means is, in a traditional data management system, think relational databases and data warehouses. That's what would be traditional. You might have concepts such as master data management. You might have data marts and various other things. You typically have a server or maybe a cluster of servers, but relatively few numbers of them, serving up the needs of your data for your company. When we move into the big data management world, when you're managing data in a big data environment, there's other challenges. Things like master data management become kind of challenging because of the very nature of it. You don't have a single cluster or server. You have a lake or a very large object store that is used to persist your data. You may also have multiple consumers of that using different technologies. And also, you don't necessarily have the luxury that you might have with traditional data management, such as a two-phase commit lock sort of experience, because we deal in the world of eventual consistency when we're talking about the big data technology, not consistency in the sense of relational data management systems. Also, we talk about parallel processing. It's not just parallel processing that big data deals with, because you can have parallel processing, and we do have parallel processing in traditional data management systems, such as a relational database system. A database server that couldn't handle more than one request at a time would not be very popular. So what we really want to talk about here is distributed parallel processing and concurrent distributed parallel processing. So what that means is that not only are things happening across at the same time on a given computer, but they're happening at the same time across multiple clusters of these things, so multiple nodes. So you may have hundreds of workers all interacting with a data store of some sort, so an object store, and your algorithms has to be able to keep those things in sync across a large number of them. Your individual project, it's not 4 to 6 pages, and it's not an electronic database document. What it is a Word document that is probably 2 to 3 pages, if that. You want to include a few descriptions of what you're doing, but basically the idea is that you'll want to use a data set that's relatively large. It's well past the 200,000 records that it says in the assignment. That was quite a few years ago. We're in millions now and growing rapidly. And you're asked to basically analyze that data set and do some relatively simple analysis. So what type of product had the most complaints ordered by state? So that means that per state, what product had the most complaints? So it can be a relatively complex query, or you can basically just do it as it's kind of implying, is that order it, group it by product complaint and state, and then order it by that as well. So that would potentially give you more information than this is actually saying, but it's a simpler way of solving the problem. Also, how many complaints have been filed for each company? So a group by the companies and the count of their complaints. And then a summary of basically talking about, for each company, what is the current state or the response for that company. So it's a couple group buys, so a roll-up essentially. You don't have to put this into what would essentially be an Access database. When you talk about a document, a database, or document, or database document, that's essentially what it is, and we don't use those. We haven't used those in a long time, a really long time. So instead, you can certainly submit a PDF of your Jupyter Notebook or Databricks Notebook. You can use different technologies than what is actually inferred for this assignment. You have to look at it a little bit, but if you take a look at subsequent individual projects, and mainly the next one that deals with analytics, it says in your previous project you used R to do this analysis. So you're intended to use R for this assignment, but I'm going to relax that to say that you can use any big data technology. Excel is not a big data technology, make no mistake of that. Neither is a traditional SQL server, nor is using something like SQLite to load in the files and then running a query against it. If you want to use a data frame inside of Pandas, I'll accept that because that's close to being what we do in big data environments. If you use SprkSQL, I'll accept that as well because it is a viable way of doing it, especially if you're doing so inside of something like Databricks. So some flexibility. You could certainly write it in R if you're so inclined. You can also use Python, assuming you use something like Pandas inside of Python. Don't write a ton of code because I've actually seen that. This should be relatively easy from a coding perspective. You are free to use the Databricks Community Edition. Whenever you go there, it is a bit tricky because, and we'll talk about it in a moment, they try to get you to sign up for some cloud trial, right? You don't have to do that. There's a free version of this for the community usage. Whenever you use, if you do go this route and you decide to use it, you want to use the code that I've got on the screen here, and I believe I've also had this as an announcement, where you basically are going to say df equals, so that's essentially a data frame, is equal to spark.read.parquet, and then the WASBS colon whack whack Allen at allenlake.blob.core.windows.net/complaints and close it up. What that's doing is reading from a open blob store that I've set up for this purpose, a file or set of files that are in Parquet format, and it's bringing it into that data frame for use. Once it's in that data frame, essentially write it out to your local instance of Databricks' workspace, which is what you're doing when you say df.write.parquet. You're saying write this data frame out as Parquet to the path that's given in the next bit, which is file store, which is a place off of the Databricks file system /table/complaints. That's the location where if you upload data inside of the UI, that's where it lands, and that's why I'm writing it there. You only really need to do that one time. After you've done that, then you can read it using the line at the very bottom, which is df.spark.read. .parquet, and then the basically the path that we use to save it initially. If you call display df, what it'll do is show you a nice little table of your data frame. It does limit it to the first 1,000 rows or something like that, so do keep that in mind. Reading is the chapter 4 out of the text, and then a relatively older article around big data storage and processing. Special topic is Spark and Databricks, and that's quite relevant for this week's assignment. Again, you don't have to use Spark or Databricks. The reason I do this is that it allows you to have exposure to a big data tool, kind of relevant when you're getting a doctorate perhaps that may center on big data. So those of you who are not big data analytics concentration folks, no worries. You feel free to use some other tool if you're so inclined. Just make sure that it kind of passes the smell test of being a big data tool. Things like Power BI and Tableau are interesting, not exactly big data tools. I might accept it, but I would prefer you to use something that has a bit more coding involved. So what is Spark? We'll start with that. And Spark is a distributed processing system. It allows you to separate compute from storage, and it focuses solely on compute. Storage is done by something else. It's considerably faster than MapReduce. In Hadoop, it's faster regardless of the situation. It is really, really fast if it's able to do it in memory, because Spark likes memory, but if for some reason it has to spill to disk, it is still significantly faster than MapReduce. It also allows you to do things like iteration. You can do loops inside of Spark, which you can't really do very well in MapReduce. There's hacks to try to do it. There's chaining together of MapReduce jobs, but it's really just not meant for it. It does, under the covers, rely on resilient distributed data sets, RDDs. That resilient bit's the part that is really interesting, as is distributed. So what that means is that if you're partway through the processing and for some reason one of the workers goes away, or you lose contact with it, then you know what data that worker has been assigned, and you know what you've asked it to do. So you can then send those two pieces of information to some other worker to pick up that work and continue. And that's the whole concept of a resilient distributed data set, is basically data sets that can be reconstructed if need be. And they also contain a certain amount of lineage. There's a directed acyclic graph involved that tells the operations to do. And they one of the key powerful things about Spark is that it supports both a batch and structured streaming sort of paradigm. Structured streaming is not the same as what we think of as traditional stream processing, but it is quite compelling and useful. In a true streaming system, the things that happen because of the arrival of data. Inside of a micro batch architecture, processing occurs at intervals of some sort. So if things start, we do some work, we pause for a little bit, and then we repeat. So that means that it's not the arrival of the data that triggers the processing, but rather a time aspect. If you want to, you can certainly install Spark inside of something like Windows Subsystem for Linux. You're going to have a few things you have to make sure you get working. You're going to need Java installed first. You might need Hadoop installed first as well. Might be able to get by without it. But basically, you go to spark.apache.org, click on Get Started, go to the download page, get the latest version of it, and then if you're running inside of a Windows Subsystem for Linux, or any Linux for that flavor, you're going to do something like wget and then -nc. You don't have to do the nc. It's no clobber. Basically means if the file already exists, you won't write over it. And then you give it the URL. That's going to download the file that's at the end of that URL. Once it's done that, you run the command tar-xvf, and the name of the tar file, zipped tar file, tarball if you will, and that will expand it out for you. Once you've done that, you can go into the various subfolders, and assuming your environment is configured correctly, be able to run them. The kind of native Apache distribution gives you essentially 3 shells that you can run. The first one we're talking about here is Scala. Scala is a programming language kind of similar to Java, but minus some of the really nastiness of Java. But what this example is doing is essentially loading into a data frame a CSV file, and then doing some simple analysis on it. So because this is Scala, not some other language, we have to declare our variables. So that's what val_df does, is declare a data frame variable, and then we assign it the return value from spark.read.format. So we're telling Spark, hey, I want to read something, and it's in a particular format, and in fact it's in a CSV format. And then we supply some options that we want to use to control that reading process. So we'll say that there's a header, and we give it the path that we want it to load. And then once it's done that, you can do a df.show, and that will display a version of what it looks like. You can also then execute a query. So this is an order by, so we're saying df.order by a particular column in a descending fashion. So we want the negative, the largest profits first, and we want the first 20 of those, and then we want to know the name and how much the profit was, and then show me that result. Similar for Spark, with some minor changes because there's language things that get in the way. But you basically go into the PySpark, start a PySpark, and that starts up the PySpark shell. Once you're inside of it, you can then run df equals and then spark.read.format, pretty similar. CSV, tell it that that there is a header via the options, and then that we want to load it from a certain location. Then once it's loaded, you can do a df.show, and then you can do df.order by, and again, ascending a profit. So the the thing we'll be seeing is the smallest ones first, and we'll only see the first 20. Similarly, Spark allows you to do queries in SQL. So you can run queries using SQL. You do so by starting up the SprkSQL shell. This syntax is a little different because of the nature of SQL. You start off by creating a temporary view using the CSV sort of format, with the options being the path and that their header is true. So we say path and we give it a relative path to the current location, and then it does have a header. Once you've done that, you've created something that looks like a typical view inside of SQL. Then you can do a select from it. So select star from companies, limiting to the first 10. And that syntax is closer to being the MySQL or ANSI syntax than it is something you might see in TSQL, where the top keyword may be in the play for that. But here we use limit instead. Then you say select name profit from companies, order by profit descending. So we're going to get the 20 largest profit companies. Databricks is an interesting product and company. It was founded by the creators of Spark in 2013. It is cloud-based. It started that way and continues to be so. It is supported by the 3 major clouds, AWS, GCP, and Azure. What they did that was really interesting is they also use a notebook interface, not that revolutionary, but they do so in a collaborative fashion. So 2 people can be editing the same notebook at the same time, and you see what the other person is doing. They also support the 3 we just talked about, Python, Scala, and SQL, but also R, so you can write R inside of Databricks if you're so inclined. One of the things that Databricks does that is nice as well is it simplifies the creation of clusters, management of them, security of them. Scaling is very much a platform as a service or software as a service, depending upon how you want to define it, but it is something where you don't have to worry about all of the stuff associated with getting Spark set up and running and keeping it running. Also supports integration with Git and various other sort of repositories so that you can do code management and promotion. A key thing to understand about Databricks is they don't make money off of their professional services to speak of. They may make some, but it's not the biggest piece of the pie. They make their money based upon you using their stuff, so they've always got an incentive to innovate and continue to make it better. So how do you get it? You start off by going to community.cloud.databricks. Sign up, but it's a little tricky, and they try their best to divert you into those top 3 bigger boxes with nice lines around them. That little gray link at the bottom is what you want. Get started with Community Edition. That allows you to start off on the Community Edition without having to sign up for any kind of a trial or whatever else, or have to pay. The Community Edition is good for what we're doing here. It's good for learning. You get a single node cluster. That means that basically there's no real workers. It's one driver, no workers, so everything happens on one box. Not truly big data, but it is a big data tool that happens to be running in a pseudo-distributed fashion. It is free. If you feel that if you see something asking you for a credit card number, you're in the wrong spot. So make sure you go back and ensure that you are careful of that. And what you see when you land on it is a blank welcome page. You'll see something pretty similar to this, except your recents will probably be empty. You'll notice in the middle the ability to drop files. That's one easy way of getting data into a cell. You may also want to do something where we do what I did before, which is create it with a data frame similar to what we did. Here's an example notebook. What this is doing is taking some data that I uploaded and then running some simple analysis on it. You'll notice that on the top we're looking at a grid of the results, the same data essentially in the bottom being visualized in a more of a pie or a bar chart sort of fashion. That's one of the nice things with Databricks is output. You can look at it different ways. It's the same data. It's just that it makes it easy. It's not going to put Power BI or Tableau out of business, but it is useful for quick data exploration, especially if you're doing something like looking at histograms or whatever else. It's pretty nice. You can upload data like I show you on the screen here. Basically what I'm doing here is taking a file, dragging it and dropping it or picking it from my file system, and I'm going to put it into that drop files here, or I may have click to browse, double click on it and open, which is probably more likely the case. And what that does is starts you down a pipeline or an experience of sort of how do you want it to do it. And you have a choice of either creating a table with a UI, or you can create the table with a notebook. It's up to you. I prefer to do it with a notebook because it gives you more control. Let's go ahead and now see if we can do a quick demo. I'm not going to click on that link because I'm not real sure what it'll bring up. Although, well, why not? Let's just see what happens. Yeah, probably nothing. One moment. Yeah, here we go. So to go back to the very top, this is where you're going to land. It looks a little bit different now than it did in the screenshot I took earlier. They've been changing things along the way. And you do have the ability to quickly import data. So they've made it such that you can pretty much go and find some data that you want to pull in. So maybe we want some CSV data. Looking for something of moderate size. And what we're doing here is I just uploaded the file, and then we have a choice of either creating it with a UI or in a notebook. We'll go ahead and do the notebook just because it gives us a little more control. You'll see here this is the place where that file was placed, and it's in that file store tables location I mentioned earlier. We're saying what the type is CSV. I am going to tell it to infer schema, and I'm going to say that the first row is a header because I know that about my data. The delimiter is a comma, and so at this point we can read it, and hopefully we gotta start a cluster up. So it has to go out and provision you a cluster. It's going to take a little bit to do that. So the way this works is that under the covers, virtual machines or containers are being provisioned and started and configured to run. And so that's what we're doing now, is waiting on it to create that. Once it creates it, we'll get back a result set. We can go ahead and scroll forward a little bit and see the next thing we're doing here is creating a temporary view that'll correspond to the name of the file. I'm going to shorten that up to something a little easier to use. And then also select from it. Notice the use of the, again, more MySQL-ish sort of backward ticks for the delimiters around the names. The reason you do that is so that they can include spaces if you want. If you're going to create a permanent table, again, give it a name, and then uncomment this code. And this code is all in Python. You can tell that up here. That's the default language inside of this notebook. And then, so you don't have to wait, I'll pause while it does the creation. Okay, we're back, and the cluster did spin up, and we can see the results of the display of the data frame. So we can now go ahead and do the next step, which is create a temporary table that corresponds to the name speed CSV. And if we do a select, it's going to look a lot like the display of the data frame up above. We can also then create a permanent table. And so one of the things you might want to do is to switch languages inside of a given a notebook to a different language. So I want to switch over and write some SQL, so to show that that is indeed working. I'm going to say select star from speed table, kick that off. You do, if you're writing SQL, you have to continually, if you're switching languages from cell to cell, you have to write the other language. The default language is going to be Python, so if there's no magic string at the beginning, that's what it'll be. So suppose you wanted to do some aggregations here, and these are things that you often do inside of SQL. So maybe we'll want to do a count and an IP, and then group by IP. And that'll show us how many different IP addresses there are. And I threw in an alias as count, and then I did a group by IP. And you can see that most of them are coming from one IP, some of the others. So you might want to do other sorts of aggregation. perhaps an average of download. And get a sense of what the average value is per different IP address. So in a nutshell, that's the kind of stuff you get started going with. From this point on, you could potentially do whatever type of aggregation if your data was complex enough that was necessary for the assignment. So after having done all that, there's a few things that you'll notice that I'd done. I did change the infer schema in the first row to true because I do happen to know that my data has a header, and I do want it to attempt to infer the data types of those values based upon what they look like. You can, whenever you go to run a command, I didn't talk that through, but you hold down and hit Shift Enter and it runs the command inside of the cell that you're looking at. You can also do so using there's this run all, handy little shortcuts up here that let you know what various things do. And so a pretty intuitive interface, but make no mistakes, it's intended for people that write code. And so these are pretty much the things that we just kind of ran through. You could also, if you really wanted to, do a run all, and that goes through and runs all the commands again. It's going to complain up here because this table already exists. That's okay, and it'll stop things whenever it hits an error, but you can continue on afterwards while hitting the Shift Enter. So an example of doing similar sort of code, very similar to what we just walked through, and with some selects and so on, and notice the use of magic commands, the %SQL. You can add cells just as I did over here by whenever you go down to the bottom, whenever you do something here and then run it, it natively puts one in. You can also do here, you can add another cell as well. You can delete the cells over here. You can also run a cell over here if you don't want to run and so on, and run ones above and below. So UI sort of quick introduction. You can use other languages, %Scala if you want to write things in Scala, %SQL if you want to write things in SQL, %Python if your notebook isn't Python, we'll make it run in Python. You can actually do so if you really want to all the time, but it's really kind of redundant. And so you can see the various kind of choices you have when you're doing this stuff. You see that what the results look like in kind of a table format, fairly common, the same sort of stuff for each one of those languages. And if we think about this stuff from a big data analytics perspective, Spark and Databricks are quite relevant because they are quite popular big data frameworks. It's hard to imagine a world without Spark these days because it is so popular. It's potentially gaining ground because of kind of a consolidation that's been occurring inside of Hadoop distributions. So the way it typically works is, yes, there's an Apache Hadoop, but there's also lots of different variations of it that are maintained and curated and extended by various companies. These companies try to make money off of licensing fees. So one of those was Hortonworks. It was a pretty powerful company, did some pretty interesting stuff, and also had a nice distribution that was fairly close to the Apache distribution, but yet they offered services such as support and favorable licensing costs and so on. Cloudera is on the other end of the spectrum, a very customized version of Hadoop. Cloudera purchased Hortonworks and then rapidly basically sunsetted all their licenses, resulting in people that are on Hortonworks having to make the choice between staying with older versions of data or of technology that may not be supported over time, or paying additional licensing costs to essentially stay on something that they pretty much already have. So part of what companies have been doing because of that is migrating onto other technologies and using things like a data lake and potentially using things like a Spark and Databricks to do that. So again, the nice thing with Databricks and Spark is that they support Spark structured streaming as well as traditional batch processing. That enables an architecture similar to like a lakehouse architecture where you have essentially a fast path for everything, and it may even be streaming of everything, but you may stream kind of once and then wait, so a very long running micro batch, maybe a macro batch, if you will. So with that, I'll wrap this up. If you have any questions, let me know. This should be enough to kind of get you going from a code perspective. Again, apologies for whatever reason that the recording didn't show up before. And as always, stay safe, and we'll talk again soon.